Okay, so today we will look at how we can construct instruction fetch unit, which is loading instruction from the memory. Okay, so here what we are trying to do is we are creating the processor. So this process can be divided into multiple stages. First stage is instruction fetch. Instruction fetch, which is loading the instruction from the memory. Okay, so there is a memory. So memory is containing the instructions. Okay, so this memory is an instruction memory. So we will divide memory into the two parts. One is instruction memory, which is containing instruction. The other one is data memory for the data. Okay, so instruction memory is only containing the instruction. And to provide the address, we have to use program counter register. So program counter is there. Okay, so we will use program counter, which is a register. So every clock cycle, the program counter will be increased by 4. Okay, so here this is 1. So we will use program counter, that is 32-bit register, generating the address, and that one is increased by 4 using the adder. So for this adder, we are providing the constant 4, and that one is, so PC plus 4 is waiting here, and we are providing the clock. So if the clock is changing, then PC value will be increased by 4 every clock. Okay, and if PC is providing the address, then instruction memory containing the instructions is returning the content of the data. Okay, so let's design this instruction fetch using the simulator. Okay, so okay. So let's try to construct instruction memory. For the register, so we have to select the register. Okay, so which one should be 32-bit? Okay. And then, so this is output value. Okay, so for the instruction memory, which one do we have to use? Which component do we have to use? So which component do we have to use? We have to use LAM or LOM, right? Which one? LOM or LAM? Yeah, LOM, because here what we are assuming that instruction after instruction is loaded, then we are not changing the instruction. So let's try to use the LOM. Okay, and so design is a little different. So here the address bit width is 8-bit, which means that the LOM size is 2 to the 8, which is 256. Maybe you can create a 32-bit, but there's nothing because 2 to the 32 is too large to support in the logic simulator, right? So simulator has to prepare in the 2 to the 32. Memory space is too much large, so it is only supporting the 2 to the 24, which is 16 megabyte. That's the largest one. But anyway, I think 8-bit is okay. Okay, so 2 to the 8, and data width is 32-bit. Okay, so output is 32-bit. Okay, so then this output is 32-bit, and this input is 8-bit. So this is 8-bit. So we are just taking out 8-bit from the 32-bit. Okay, so which component do we have to use in the case? The bus width is 32-bit, among them, we are just taking the 8-bit. Which one? So in the wiring, there is a splitter. Okay, so we will use splitter. Splitter is actually splitting. Okay. Here, this one is like this. The input bit with 2-bit, but actually we have to support 32-bit input size. Okay. And then among this 32-bit, how many bit we have to take in? How many bit? 8-bit, right? So fan out is two or three, well, we don't know that. So from 0 to 15, 16 to 31, so which index should be connected to this one? So it's totally depending on the 0 is the largest one, 31 is the smallest one, where is the opposite, right? So anything is okay. But what we are doing is we will use, so this is 31 is the largest one, and 30, and let's assume that the 0 is the smallest one. Okay, so then this address is representing 1 byte, right? But here, the long case, the output is 1 word, it's 4 byte, right? So if this is 0, then we are taking the 0 word. If this is 4, then we are taking this one. 8, we are taking next one, right? Okay, so just try. We are ignoring the last 2-bit. Last 2-bit is not used. So let's say this is 3 output, and last 2-bit is ignored. And from 2-bit, and from here it is actually, let's say this is single one, and we are not using this thing. And from 1, 2, 3, 4, 5, 6, 7, 8, from bit 10 to the 32, 31 will not be used. Okay, so we will not use this part. So then you can see that only from bit from 2 to the 9 is coming out. So we are connecting this one, and then this is connected to the input. Okay. So among the 32-bit, we are taking the 8-bit only from 2 to the 9. Maybe if this is 1, this is not there. This one. Okay, so then we have to increase this one by 4. So to increase this, we are using adder. So input. And adder is 32-bit adder. Okay. And also we are providing the constant 4-bit. Constant 4. This is also 32. 4 is what? This is 4. 100, that is 4. Okay. So if we are looking at the value, you can see that it is 4, right? 0 plus. Okay. So for the debugging part, we are feedbacking that one. And let's look at the output value. It is also starting to be. So currently containing value is 0. Maybe you can change it, but I think my one has some problem. So it's not working correctly. I don't know why, but maybe in your computer system it will be working. Okay. We are providing the clock. And instead of using this part, let's use the constant. Okay, so constant. And this one is also 32-bit. And value is 4. So if we are triggering it, then it is increased by 4. Then the next word is chosen. It's not next word, next byte, I think. Let's look at it. Okay. I think in the here case, it is byte addressable. So let's see, this is 0. This is 1. Okay, so this is byte addressable. Okay. So when it is triggered, then next address is next word is chosen. Okay. Next word is chosen. Okay. So here, let's say this one is insertion. So this is current PC value. So PC value. PC out value. Actually, PC plus 4 value. This one. And the name is insertion fetch. So can you create this insertion fetch unit? Maybe you can also provide some clear to initialize it. This is triggered, then it is starting 0. You have to make this one very carefully because we have to use this component to construct the processor. During the designing, if you have a question, please let me know. Sorry to bit, I'm on the 32-bit why we are taking the last 8-bit because the address bit width for this LOM is 8-bit. That's the only reason. If we are increasing this one like 10-bit, then we are taking the 10-bit from the address. Okay. So actually, if we can connect all the 32-bit to this LOM, that's the best. But actually, the maximum size of this LOM is only 24-bit, so small size. So that's the reason why we are just using this splitter. Okay. So anyway, PC register is 32-bit, but the memory size is smaller than the 2 to the 32. That's the reason. Do you got it? Register, why we are not using the 8-bit as a register? Because this PC will be used for another register. Okay. So like a jump and link, or like a jump or branch, this will be based on the 32-bit. So basically, we are using the 32-bit for every register. So actually, the best one is that we have to use the 32-bit instruction memory. That's the best one. But for the simulator limitation, we are just using this splitter. So in my simulator, there is some problem. Actually, this one has some problem, I think. Some let me show you. Okay, so this is a different one. Bit, wiring, splitter, connection. Splitter is 32-bit, single pan out. Everything is done. Mini AP disconnected. And then there's the header. Which one is 32-bit? There's a constant. Which one is 4? And this. Let's reset. And clock. Let's look at the output. And let's change the data. Change the entire data and if I'm changing it, so here this is the behavior of working of this component is different. So this case, last two bits should be appended, and some more two bits should be selected. So it is selecting the next word, and then it generates the output. So this is hexa value. Okay. If I'm okay, next one, next 4 bytes are coming out. So this is 1, 1, 1, 1, 0, 0, 0, 0, 72 bit. So here in this case, what you have to do, you have to give last 2 bits should be appended and more 2 bit is generated. Okay. So 8 bit is provided, but using that 8 bit, it is selecting the 4, it is selecting the one word among the to the 8 word. And this is instruction. So everyone is completing this component. Please let me know if you're done. So if this LOM is not working, then just remove it. And then if you redraw it, then it will be working. Okay. So if it's not working, then just redraw it. Maybe then it will be working. So I had a problem, so now it is working. You can withdraw it. And this is something full, so if it's 10 bit, then last 2 bits should be ignored. And 2 bit is added. If we are the 10. Okay. Then, so this is instruction fetch. Now, what we'll do is we are constructing the MIPS processor. So let's create MIPS processor. In the MIPS processor, we'll use this instruction fetching. Okay. So it's clear. Next page, instruction. This will be sorry. So if we are clicking, I mean, giving the clock, so clock, one more clock, and you can see that this is changing. In the menu, there's a simulate T1s. If you're clicking this one, then you can see that the pitch value is increasing, and also clock, I mean the next clock is next pitch value is increasing. You can see this one, and we can do clear. So the first one is instruction fetch. Next one is what we have to do is we have to analyze this instruction. Okay, so it's a 32-bit. So how we are analyzing? First, we are supporting the ALU type instruction. So do you remember the format of ALU type? What is the first 6-bit? That is called first 6-bit. Yes, OP code. Right, and then 5-bit is OP code is 6-bit and RS. This register 5-bit, RT is 5-bit, and LD is 5-bit, and then amount 5-bit, and last 6-bit is function. Right, that's the alphabet. Okay, so what we have to do is we have to analyze this 32-bit into the this category 1, 2, 3, 4, 5, 6 categories. So to split it, we have to use this splitter. So we are splitting this 32-bit into the 1, 2, 3, 4, 5, 6 cases. Okay. So this will be changed to 6 cases and bit with this 32-bit. Okay. So first one, so this 5-bit from bit 31 to the 26, this much. This is OP code. Okay, so this is OP code, and then RS 5-bit 1, 2, 3, 4, 5. This is second one is RS, and this one is RT. 1, 2, 3, 4, 5. This RT, and then this is RD. 1, 2, 3, 4, 5. And then this is shift amount 5. Something is missing. Okay, this is 6-bit. Okay, so the last one is OP code, and this is RS, this is RT, and this is RD, shift amount, and this function code. Okay, so we can categorize each bit. So can you create this schematic? So this is 5-bit. OP, RS. Someone is asking me about the instruction fetch. So let's go back to the instruction fetch unit. Okay, so this is a 32-bit register. What is your question? Isamit, what is your question? Which component do you want to see? Instruction fetch or MIPS processor or which one? Next PC. Next PC is not required. This is not required. You can remove it. Anyway. It's just output. So this is not required. If we are clicking it, so the RS is changing. Okay. So what component we have to create is we have to make REST file. Okay, you can use one. How you can do that is in the menu project. Then you can add a new file, right? So let's try to add new file. So project as a circuit and add REST file. Okay. Um, so let's try to create this REST file. I'm just asking, did you finish to create this REST file or not? Maybe you are not, right? Did you finish or not? Can you type in the chat window? If you finish, file. Okay. So somebody is creating and somebody is not creating. So if you already has the REST file, then you have placed the REST file here and connect RS, RD, RT, RS, RT, RD into the REST file. If you are not, then let's try to make it. REST file, what you have to do, we don't have enough time, so let me just simply creating it. So I'm just creating the 2 register. Actually, I have to copy 32 registers. And I'm selecting the output, which is data is 32-bit, selection bit is 5-bit. It's very large. First one is here, and this should be 32-bit. This one is so 32-bit. Okay, so you have to connect everything. Anyway, and there is output. This 32-bit. Okay, and selection bit. It should be 5-bit. And this is first one. maybe it's not easy to draw. And here, which this one is on. And this is second. Let's see. Then for the writing, we have input, which is 32-bit data. So this is connected to the input port. And also we have to choose which register is updated. So let's use multiplexer. Enter is 1 bit. Selection is 5 bit. And the input is, there's 1 bit input, which is saying this is writable or not, load. And also you have to give five bit for destination. First one is and we have to connect to the clock. So this is a figure of the register file. So everybody is creating this file. So if you are completing it, then what you have to do, you have to go to the MIPS processor and creating this register file. So it has RT, RD, RS. So first one is RS. Then it has some problem, but then RS. Second is R. This one is R. T. And this is RS, RT, RD. This is load, and this is input C. And this is B, and this is A. So let me show you. This is A. And this one is B. And here, this will not be working because if you are because inside this list file, we are just adding two registers, right? 0 register and 1 register. We didn't draw it, everything. So it's not supporting every case. So instance here, all the RS case. Let me show you. Oh, it's not, sorry. So it's only supporting 0000 or 0001 case. So let's go back to the instruction page. Let's change the instruction. So let me change the instruction for 0. Then go back to the MIPS register. So let me reset it. So then you can see that the RS register is 0, so output is 0. Okay, this is coming up. 0. So can you do this one? So this one is decode stage. So what is next step after we are reading the register value? What do you think about it? So next stage is computation, right? So receiving this input, and we are doing some operation like addition, multiplication, and or that result is going back to the register again. So here we have to do execution stage. Next. So for this execution, what do we need? We have to have ALU. So let's create new circuit, which is ALU. So ALU. So using simulate project and add circuit, creating the ALU part. And here, actually we made it, but anyway, let's try to make it. So we can support add, so 2-bit, input and output, 2 input, one, and one up. So in some case, we are using this addition, or we are supporting the subtraction. Subtraction, or we can support gate logical things like and, or like that. So data bit is 32-bit, and number of bit is 2, and this one also 32-bit, 2 inputs, 2-bit inputs, and small size. And we have to add multiplexer to select. Oh. So let's try to select using the data output is a little bit. Selection bit is depending on how many operations we are supporting. So if we are supporting 16, we are using like this. Okay, maybe It's depending on which one is connected. This is a 1, this is a 3, and this is something. This is another one. Nor is like a 0. It's totally depending on which function is actually used for the name. So this is actually function. Which operation is selected. So this is ALU. So can you make this ALU? So if we are completing this ALU, then the next one is, let's go back to the MIPS 1, and you are connecting this ALU. Okay. This is A. This is B. And this is function. Function, we have to provide it. Actually, this function is from this instruction, but currently we don't have the one. So manually we are giving the function. And later, actually, this will be automatically created from the automatically created. And the output, C, is actually going back to the register update. Okay, so this output, ALU output, is going back to the register input. And here, this is also automatically generated, but let's give it manually. So let us assume that this is 1. So load signal is enabled. Okay, so let's look at what is the output. This is, let's look at what is this output. So function is 0, case, 0 nor 0 is 1, 1, 1, 1. So this is input for the next one. So if we are changing the clock using this clock tick, okay, so this is not available because of the instruction. So let's go back to the instruction. And let me change it. The second instruction is also 0. Okay. So let's go back to the MIPS processor and reset it. So instruction register should be also reset. Counter is not reset. So anyway, after the instruction is executed, then register 0 is updated by 1. So that is coming out. Okay. And collected. Okay, so then 0 is stored here. So coming out, 0, nowhere 0 is 1. 1 is waiting here. Okay, if I enabling clock, then this value is updated to the destination. So the destination register is RD. RD register. This is 5-bit. So if I'm clocking, then this 1 will be updated to the register 0. So can you draw this one? Okay. So next time, so today we are just creating this MIPS processor to support all type. Okay. So next time we will look at the how we are supporting I type. I type instruction. So add I will be supported. And if you have time, then you have to completing the inside of register file and inside of this ALU. So the mux things is depending on this function part. So it's totally depending on your decision actually. So how many components is supported is your design choice. Okay, so the next time we'll continue about the I-type implementation. So after that, we will look at the load store, and then we are supporting the jump instruction, branch instruction. Okay, so see you next week. Bye.